Namaskar. I am Dayan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss isoperimetric problem related to the variational principle from classical mechanics of MSc1 and semester first. The problem in which the function which is eligible for the extremization of a given definite integral is required to conform with certain restrictions that are given as the boundary conditions. Such problems are called isoperimetric problem. The method is exactly analogous to the method of finding stationary value of a function under certain conditions by Lagrange's multipliers methods. Theorem for isoperimetric problem. Obtain the differential equation which is satisfied by the functional f of x y dash, which extremizes the integral I of y of x is equal to x1 to x2 f of x y dash dx, subject to the condition y of x1 is equal to y1, y of x2 is equal to y2, and the integral j is equal to x1 to x2 g of x y dash dx is equal to constant. For proof, consider the functional between 2 points p of x1 y1 and p of x2 y2 given by I y of x is equal to integral from x1 to x2 f of x y dash dx, subject to the condition y of x1 is equal to y1 and y of x2 is equal to y2, and j is equal to from integral from x1 to x2 g of x y dash dx is equal to constant. Consider in xy coordinate system 2 points consider, and from 2 points a1 curve passes through p and q, and now this curve is equal to y of x, and y is equal to y of x plus epsilon 1 eta of x, eta 1 of x plus epsilon 2 eta 2 of x. The points P and Q can be joined by infinitely many curves according to the value of the integral I will be different for different paths. Let all possible paths starting from P and ending at Q be given by two families of parameters, family of curves. Y of x is equal to y of x plus epsilon 1 eta of x, eta 1 of x plus epsilon 2 eta 2 of x, where epsilon 1, epsilon 2 are parameters, eta 1 of x, eta 2 of x are arbitrary differential functions of x, such that eta 1 of x1 is equal to 0, eta 1 of x2 is equal to, and eta 2 of x1 is equal to 0, eta 2 of x2. This condition ensures that the curves of the families that are all passes through the point P and Q. Note that we cannot, however, express y of x, capital Y of x, as merely one parameter or one parameter families of curves, because any change in the value of the single parameter would in general alter the value of j, and is given by I of epsilon 1 epsilon 2 is equal to integral from x1 to x2 f of x y dash dx, and j of epsilon 1 epsilon 2 is equal to integral from x1 to x2 g of x y dash dx is equal to constant, and this is j of epsilon 1 epsilon 2 is equal to constant. Now see here, where lambda is a Lagrange's undetermined multipliers. Therefore, f star is equal to f plus lambda g. The extremization of 1 subject to the condition 3 is equivalent to the extremizations of 9. Thus, from differential equation calculus, the integral r star is extremum if del by f star divided by del by epsilon j is equal to 0. This is form of 9 equal del by f star by del by epsilon j is equal to 0. This is integral from x1 to x2 del by f star by del by y eta of x plus del by f star by del by y star del by y dash y dot eta j dash of x dx is equal to 0. Note that epsilon 1 epsilon 2 is equal to 0. Integrate the second terms by parts, therefore, and this way integral from x1 to x2 del by f by del by f star by del by y minus d by dx of del by f star by del by y star y dot eta of eta j of x dx is equal to 0 by basic lemma of calculus of variations. Del by f star by del by y minus d by dx of del by f star by del by y dot is equal to 0. This is required Euler's Lagrange's differential equations to be satisfied by y of x, for which functional I has extremum value under the condition. Generalized theorem. Euler's Lagrange's equation for several dependent variables. Now see here and so on. Next theorem. Obtain the differential equation which is satisfied by the 4 times differential equations y of x which extremizes the functional I of y of x is equal to x1 to x2 integral f of x y dash y double dash dx subject to the condition j is equal to x1 to x2 g of x y dash y double dash dx is equal to constant and both y and y dash are prescribed at the endpoints. Now see your theorem, similarly previous theorem and so on and so on. Example now see here. Find a plane curve of fixed perimeter that encloses maximum area. The problem is supposed to arise from the gift of a king who was happy with the persons and promised to give him all the land that he could enclose by running around in a day. The perimeter of path was fixed. In a circle, a king was introduced a price of land that running in a day. एक राजा होता आणि त्या राजानं असं प्रमाण काढलेलं होतं की एका दिवसामध्ये एका दिवसामध्ये सर्क्युलर फॉर्ममध्ये जो जेवढी जमीन क्रॉस करेल तेवढी त्या माणसाची जमीन मी देणार आहे. आणि मग हव्यासापोटी हव्यासापोटी ते लोक पळत धावत सुटले आणि शेवटी त्यांना डेट आली, मरण आलं. आणि मग अशा तऱ्हेनं हव्यास बरा नाही आहे, आपल्या कोवती एवढंच आपण काम करू किंवा आपल्या कोवती एवढंच आपण डिमांड करू असं जर त्या लोकांनी हे केलं असतं तर राजाने त्या जमिनी त्यांना देऊन टाकल्या असत्या. परंतु हव्यासापोटी प्रत्येकजण आपल्या आपल्या ह्यानं ते पळतच धावत सुटलेले होते. दिवसभर धावत सुटले आणि त्यामुळे रनिंग करताना त्यांना ते मरण आलं. असा जो प्रॉब्लेम आहे, फाइंड द प्लेन कर्व ऑफ फिक्स्ड पॅरामीटर दॅट एन्क्लोजेस मॅक्झिमम एरिया, हाच तो प्रॉब्लेम आहे. आणि दिस इज ॲप्लिकेशन ऑफ मॅथमॅटिक्स इन रिअल लाईफ. Solutions: let y is equal to y of x be a plane curve of fixed parameter L. L is equal to x1 to x2 integral from ds, where the infinitesimal distance between 2 points on the curve is given by ds square is equal to square root of 1 plus y dash square dx, where y dash is equal to dy by dx. Hence, the total length of the curve between 2 points P and Q becomes integral from x1 to x2 square root of 1 plus y dash square dx is equal to L. The area bounded by the curve C and the x-axis is given by a of y of x is equal to integral from x1 to x2 y dx. Thus, we maximum subject to the condition integral from x1 to x2 square root of 1 minus 1 plus y dash square dx is equal to L. Hence, it must satisfy Euler-Lagrange equations d by f star by d by y minus d by dx of d by f star by d by y dash is equal to 0, where f star is equal to f plus lambda g. F star is equal to y plus lambda square root of 1 plus y dash square. Solving this form, d by f by d by y is equal to 1 and d by f by d by y dash is equal to lambda y dot divided by square root of 1 plus y dash square, and minus 1 minus d by dx of lambda y dot divided by dash divided by square root of 1 minus 1 plus y dash square, and completely solve. Therefore, x minus integrating lambda y dash divided by square root of 1 minus y dash square is equal to a constant of integration. Solving this for y dash, and y dash is equal to x minus a divided by square root of lambda square minus x minus a bracket square. We put x minus a is equal to lambda sin t. Therefore, dx is equal to lambda cos t dt, and therefore y is equal to square root of integral of lambda sin t dt plus constant of integration b. Y is equal to minus lambda cos t plus c, and so squaring equations, x is equal to x minus a is equal to lambda sin t and y is equal to minus lambda cos t plus b, y minus b is equal to lambda minus lambda cos t. Therefore, x minus a bracket square plus y minus b bracket square is equal to lambda square sin square t plus lambda square minus cos square t plus sin square t is equal to 1. Therefore, x minus a bracket square plus y minus b bracket square is equal to lambda square. This is circle centered at BB and of radius lambda, and is to be determined. And to determine lambda, we know that the circumference of the circle is 2 pi lambda. 2 pi lambda is equal to L. Therefore, lambda is equal to L upon 2 pi. This is maximum area enclosed problem.